So I'll pick up the last, words by Doug saying that about the complexity of the aerosols, and I will add a little, few more dimensions to that. So what we do, it's kind of different approach from, Doug and the MS community where they bring instruments to the field and so on. So we collect samples, okay, and bring the samples to the extensive laboratory studies. And the topic of my presentation is chemical imaging and molecular characterization of aerosols. And I will try to give you an overview of what kind of the studies can be done with the samples of aerosols. Okay, so how can I advance this? Is it like this? Oh, okay. So, in principle, different types of the instrumentation or chemical analysis can be applied for the analysis of aerosols, and this is kind of the schematic presentation of different approaches that we use. So we use, the range of the approaches from the microscopy visualization, like electron microscopy, X-ray microscopy, and then the different types of the spectral microscopy techniques, and up to the high-resolution mass spectrometry that we can also do from the collected samples. The thing is, of course, that the matter is really complex, and there is no any silver bullet technique that will give us all the information that we want. So the microscopy techniques are great. I mean, they can visualize, they can show you the particles the way they appear, their sizes, their internal heterogeneity, and so on. But they are really not powerful in terms of the molecular level characterization. On the other hand, the modern methods of the high-resolution mass spectrometry has tremendous power for analysis of individual molecules. But of course, I mean, they require a substantial amount of sample. It cannot be done on the basis of single particles. And the approach is, of course, to try to apply as many techniques as possible and try to learn as much as possible about these properties of the aerosols. So with these techniques, again, I mean, we can, on one side, it's really material contrast and elemental composition, chemical state, and mixing state of individual particles, and then molecular level characterization of complex organic matter. So, as I said, here we apply this end of the techniques to learn morphology, shapes, internal heterogeneity, and the individual properties of particles, and we characterize the organic material by the application of high-resolution mass spectrometry. So the topic that I choose to, the kind of scientific topic that I choose to talk today a little bit again, this is the phenomena of brown carbon aerosols. So, they're mainly formed in the as a products in the biomass burning, as Doug already noted. So all the organics in the atmosphere, I mean, they can be sort of sorted out based on the refractiveness and the light absorption properties. So we know that the most absorbing material, carbonaceous material in the atmosphere, this is of course the black carbon, and this is a major absorber that absorbs light with the lambda to -1 power dependence. So, and these are the the structures that absorb light. I mean, chemically, I mean, they're kind of boring. I mean, it's soot. This is graphitic layers of the carbon, and from chemical point of view, this is a well-known system, and its properties can be predicted and explained. So then we have the whole bunch of the gas phase organic species that absorb only in UV, and then in between we have this really poorly defined material which is called brown carbon, which has variety or different absorbing characteristics with different dependence on the wave number. And actually here we are talking about the whole book of the organic chemistry. It could be anything. Okay, and in that regard, of course, predictive understanding of the optical properties of brown carbon really relies on the fundamental knowledge of its composition and atmospheric chemistry. So, this is just the illustration of the impact of the brown carbon in highlighted in few works of group of Relanatham, starting from 2007 in JGR, and then more recent paper in PNAS, showing that at some specific locations of the world, some specific geographic locations, the contribution of the brown carbon overall would be half of the black carbon. So still, black carbon is the major absorber, but brown carbon is the substantial or significant player too. So at this point, it's really very little is known about the composition, the origin and sources of brown carbon overall. And what is most important, it's really unknown what's happening with this material as it undergoes atmospheric transformations and atmospheric aging. So, as I already said, the major source of the brown carbon is the biomass burning, the fuelless material released in the biomass burning. And depending on the fuel type, so the chemistry of this material, even in the primary source of the biomass burning, will be quite different. So for years, it was kind of the major conclusion that it's all about the biomass burning, but there is a growing number of literature and recent papers, showing, in different laboratory setups and so on, so that actually the SOA material that is, formed as non-absorbing, so over the time of the atmospheric aging, may become slightly absorbing too. And the examples are, the photooxidation of pHs, formation of the nitrated aromatic molecules, oxidation of aromatics by OH in powdered water, condensation of carbonyls, some reactions of the carbonyls and ammonia and amines. And the list of these studies is really growing as we speak. So there is this second source of the brown carbon that is not fully understood at this point and even not fully recognized. So, comparing the properties again, black carbon versus the brown carbon. So, the formation of black carbon, it's always combustion. Okay, so the part of the brown carbon is also comes from combustion, but kind of poorly controlled combustion, like not, the let's say engine combustion. It's mostly really uncontrolled burns or forest fires. And then there is some, really unknown yet, but various mechanisms of the secondary brown production. Now, the interesting thing is that, these two sources, the black carbon and the primary brown carbon, they are light absorbing at the time when they emitted in the atmosphere, but the secondary brown carbon may appear later after the emission. Still, the typical values of the mass absorption coefficient are substantially higher for black carbon. But again, for specific geographic locations, the contribution of brown carbon is not negligible. Now, what is really important here, and this is a major difference between the black carbon and the brown carbon, is that once the black carbon is emitted, its optical properties do not change much. So as I'll show you today, and there are many papers showing, recent papers showing this effect, that the brown carbon material is very highly dynamic system. It can be formed in the atmosphere, it can be destroyed in the atmosphere. And the aging and evolution of the optical properties of brown carbon is really understanding this process requires fundamental understanding of the chemistry of this material. So, coming to the chemical imaging options and studies of the brown carbon materials by means of electron microscopy, this is one of the probably first types of the brown carbon material. These are the tar balls, so-called tar balls from the biomass burning. So they're quite a few publications showing this type of material. So what is nice about the application of this technique is, indeed, we can see the morphology of particles, we can see their size, we can see how abundant they might be in the population of the sample particles and so on. And then there was also very, I would say, clever and neat study where the yield spectroscopy spectrum of these particles were converted through some theoretical assumptions and so on directly to the refractive indices of individual particles, as a function of, determined as a function of the optical wavelength. Now, while that paper was really made highlights and everything, so in fact, there's a problem with this type of the approach, because to make this type of a measurement, or to make this type of the, let's say, the calculation of the refractive indices, you need quite a few requirements. So first, these particles, they need to be non-volatile, so they stay in the microscope. They need to be stable under the electron beam, so one can collect the spectra. So the theoretical considerations here require some assumptions on the particle morphology. So in this case, it was very easy, it's spherical. So, and then also it requires the homogeneous internal composition for these assumptions. And then finally, it also requires small size, so that the electrons, they go through the whole particle and the same, this spectra can be collected. So in this regard, it was kind of, nice, it can be done, but, the number of, lucky requirements that one would need to do such type of analysis is kind of long, and, for many systems, it's not terribly practical. So anyhow, in this regard, the optical properties of the brown carbon really, the measurement of the optical properties relies on the bulk techniques and the optical techniques, optical measurement techniques. So Rebecca will be talking about it later today, I think, right? So now this is just another illustration of similar type of the brown carbon, also roundish particles. They're substantially larger than the tar balls, and we don't know yet the exact origin of these particles. We kind of call them anthropogenic brown carbon, and we believe that they may have been formed in some anthropogenic sources. So with the X-ray technique, we can really get the spectral signature of this material with lateral resolution. So we see the carbon-carbon double bond, the carbonyl form of carbon within the individual particles. These are particles substantially larger than the tar balls that I showed. And again, these are very important assumptions for the modeling of the optical properties, for understanding what kind of the bonds or chemical information contributes to the light absorption of this particle. So in this particular case, it's very similar to the tar ball particles in terms of the morphology and the composition. So, but still, it's somewhat different. The ratio of the carbonyl and the double-double bonds is different from the tar balls. But again, this is nice and interesting system, and can be also simplified. So we hope that we will be able to retrieve the optical properties from this system as well. But unfortunately, the reality is quite different. At the time when when the bulk instruments, they measure so-called brown carbon material appearance, in specific time periods. I mean, the real picture of the particles might be something like this, where everything is mixed together. So the particles may include the brown carbon itself. This is the red inclusions. Then it may include some sort of light absorbing organic material and some organic material and so on. So in fact, yes, and these applications of the chemical imaging techniques are useful, and they may give very important results. But for highly, let's say, for simplified systems, and understanding of something like that is really, what we need to do, and we need to develop techniques for, future research. So now let me switch gears a little bit and talk about the molecular characterization of the brown carbon material. So I'll be talking about the laboratory-generated system. So this is the oxidation of phenol or toluene in the presence of NOx and OH radicals. And what happens here, also the system has been studied by quite a few groups, but here's our recent addition that just appeared on the website of PCCP. So at the high concentration of NOx, so the resulted material, the resulted SOA from this single precursor really has substantial brown carbon properties. This is the plot of the mass absorption coefficient taken of the material without NOx. This is the black dots, and this is with the presence of NOx taken shown by red dots. And so to understand what's going on and why, in one case it turns, the resultant material is brown, and in another case is not, we started to do some comparative studies. So where we generated this type of aerosol, we generated this type of aerosol, and then we did quick analysis of the overall material which is formed in each of the cases. So what we clearly saw that in the case of the brown carbon appearance, we see lots of nitrogen-containing compounds. So that gives us, first hint that so the incorporation of nitrogen into the SOA material probably plays a role in the formation of brown carbon. But of course, we have thousands of different products, and only some of them may absorb light. Not necessarily all of them. They contribute equally to the phenomenon of brown carbon. So what we did next is again, in this case, we need substantially more amount of the material. So this is solution of the brown carbon material. So, and then we applied the separation, HPLC separation, followed by the UV detection and the high resolution mass spectrometry. And we did the correlated analysis of mass spectra and UV data obtained from this tandem approach. So what I show you here, this is the kind of two-dimensional plot of the UV data. So this is the retention time or separation time on the column. So these are the wavelengths, and the colors that you see here, these are the intensity of the UV's spectrum. So then, we can correlate the appearance of, let's say, specific peaks or specific bands of the light absorption with the different ions separated on the columns, and then come to conclusions of what kind of the compounds or what kind of the materials are responsible for specific moments of light absorption. So, the assessment of molecular structure. So, let me step back. With the high resolution mass spectrometry, we get a very clear idea about the elemental composition of specific peaks that would coalesce or will show up at the same time with the appearance of specific bands. But the assessment of the molecular structures from this elemental formula is quite a challenging task, and so the first thing, if there are some standards, they can be compared, and then by comparison, it can be really suggested, or specific molecular structure can be reasonably determined. But in reality, of course, even for these, for the toluene system, the system, the resultant number of products is so many, and the system is so complex that it's really lucky case when we can get anything to confirm with the standard. So then, we can also suggest some of the molecular structures by the means of theoretical chemistry calculations. But of course, it's a long time process. It also needs to be driven by some hypothesis and so on. So anyhow, the truth is that most of the assignments here, they are educated guesses and based on intuition. And then, of course, there is some feedback always between our guesses and possible theoretical calculations that can either confirm or deny our guesses. So, but nevertheless, this approach gives unique opportunity really to digest the brown carbon material and say, what type of the chromophores, may be responsible for specific light absorption. Now, so by doing this exercise, we can sort of digest the brown carbon material and basically break it down to the contribution of different chromophores. So this is the plot of the overall absorption by this material, the brown carbon from toluene and SOA. And what it turns out that actually half of it can be really attributed to the light absorption just by a handful number of chromophores. Now, once we know, those chromophores, and we can say something specific about their possible chemistry and formation, we can sort of start to develop predictive understanding of the brown carbon property. So, yeah, the other system I was talking about, the brown carbon and toluene SOA. So this is another example of the methyl glycol and ammonium sulfate brown carbon material. So this is the material that is formed in the aqueous chemistry of methyl glycol. The same thing, and substantial portion of the light absorption by this material can be really attributed to the absorption of selected chromophores. Now, here's the thing. I was talking so far about the laboratory-generated system. Even that system is quite complex, and it's hard. It's an effort to digest the brown carbon information and so on. But of course, the brown carbon material from biomass burning is even more complex. But nevertheless, it can be really, by using this technique, we can separate different light absorbing, let's say, components of this material, and this is our ongoing work. So some of them, the most prominent chromophores we can identify right now. So again, I would say that this approach is applicable and hopeful for the understanding of the field samples as well. Now, so once we have, kind of at least the initial understanding of, good idea about even not the exact molecular structures of the chromophores, but their types, and we can select them and do some model or, let's say, laboratory study to see how they would behave in the atmosphere. So this is an example of one of the studies we do in collaboration with Sergey. Actually, these are studies that led by his group. So one of the types, of the brown carbon that I just showed you, it's very similar to the toluene SOA. So once the brown carbon is formed, it's very stable. You shine the light on it, and yeah, you can photo bleach it, but the effective time of the photo bleaching in this case takes like a couple days or so. Now, the other type that I also just showed you, this is the methyl glycol and ammonium sulfate mixture. So this is unstable system. So in fact, the color of this system can be bleached away within minutes to hours in the atmosphere. And there is even more interesting system, of the nitrophenol-based specific chromophores. In this case, this is the dinitrophenol, I believe. So in this case, upon photobleaching, the absorption decreases in the UV region, but builds up in the visible region. So with that, I just want to say that all these chromophores, I mean, they're chemically different, they behave differently. And understanding, these differences and the relationship between the composition of this material and its optical properties really needed to advance this research. So with that, I just give you some conclusions from our observations. So we believe that strong chromophores at low concentrations contribute substantially to the light absorption by brown carbon. So we know now that there are primary and secondary sources of brown carbon. And again, brown carbon, this is the material that evolves all the time. And to understand, how this would behave and how these properties would evolve requires fundamental chemical knowledge. So with that, this is just, a few notes about where we go right now, with all the knowledge that we accumulated so far. So we think that, that common and source-specific DRC components or chromophores need to be identified and compared between different materials with different sources. So, and then we would like to study how they would behave as a function of time. So all that we showed here, it's again, I mean, this is the laboratory measurements. So it's all with absorption spectroscopy and correlation with the mass spectrometry. But the aerosolized material, needs to be really measured, and optical properties of this material needs to be measured in its atmospheric state, like in aerosols. Of course, there is a challenge of quantitative detection of individual components or chromophores of BRC within complex organic mixtures, and there is lots of work needs to be done to advance the analytical techniques towards this goal. And again, as I already noted, so what is the effect of different internal particle composition on the overall optical properties? It's also the area. It's actually an untouched area in many ways that also needs to be explored. And with that, this is my last slide. So I just want to acknowledge the work of people whose results I showed today. So this is our group in DMML. So the microscopy studies we do in close collaboration with the group of Mary Gillis, and photochemistry and mass spectrometry work we do with Sergey and his students. And with all that, I'll be happy to take any questions.
Can proceed to the orange chair.
I request all the session speakers to please